Hello and welcome to this month's edition of Standard Motor Products Power Hour. This month we are sticking with the topic of air conditioning, and the specific topic we've chosen for this month is electronically controlled variable displacement compressors. These are compressors where the pumping displacement, the actual pumping output of the compressor, is completely computer controlled, and we're finding there's a lot of misunderstanding and misdiagnosis associated with these compressors. So let's take a look at what we're going to talk about today in this session. Three pieces of the conversation we're going to talk about today is these electronically controlled variable displacement compressors, how they actually work, how they function. We're going to talk about diagnosing them, some diagnostic approaches. How do I confirm, is there a problem with the compressor or not? Does it actually work? And as we go along throughout the session, we will share some service tips as we get into it. So if you look at one of these compressors, here's a typical one. If you look over on the right-hand side here, there is an ECVD solenoid. That's the electronically controlled variable displacement solenoid. And I actually have a couple of these compressors on the cart here in front of me. So let's take a look at them. They look like a pretty conventional compressor. The first ones, the very early ones, early Europeans, Asian, and some mid-2000s Chryslers were the first to use this compressor. And the first thing I want you to notice here, that this compressor does not have a conventional clutch. If you see when I turn the pulley, the crankshaft of the compressor is turning all the time. And if we look behind the curtain here, if I look in the back of the back of the pulley, you can see there's actually no clutch. There's no electrical clutch on this compressor. And this means that even when it's 40 below and the air conditioning is off, the crankshaft of the compressor is still turning. Now, to control the output of these compressors, there is a solenoid in the rear head. This electronically controlled variable displacement solenoid, the computer can vary the pulse width command to this solenoid to change the stroke of the pistons inside to change the output of the compressor. So, so the early ones, as I said, had no clutch. However, in more recent years, some manufacturers, it depends, some manufacturers have now started including a conventional clutch. So if you'll notice as I turn the pulley here, the center, the hub, the crankshaft is not turning. So, of course, when the clutch engages, just like a conventional compressor, now the crankshaft is turning. However, it does still have, as you can see in the rear head here, it still has the displacement, the actual output, the pumping output of the compressor is completely computer controlled by the solenoid here, by the ECVD, the electronically controlled variable displacement solenoid. So to get a better sense of how these compressors work, we're going to look back at an older technology. And so let me put this away for just a moment, and I'm going to grab an older, this is an older GM V-series compressor, as you can see here. This is a relatively old technology. It's been around for many years. But the ECV, the electronically controlled variable displacement compressor internally is very similar to the way this older design works. So as you can see here, when I turn this compressor by hand, here are my pistons. This is my piston right here. And you can see that as I turn the compressor by hand, the piston is going back and forth pretty easily, right? Now, what's unique about this compressor is it's got we call this a wobble plate on this older design. Most modern systems, we call it a swash plate. And do you see that if I change the angle of this swash plate, there you see I can change the angle of the swash plate relative to the crankshaft. I can set a right angle to the crankshaft, or I can turn it at a bit of an angle, more of an angle to the crankshaft. So here I've set the swash plate or the wobble plate perpendicular, or more or less at right angles of the crankshaft. And now watch what happens when I turn the compressor. You can see that the pistons hardly move at all. If I adjust the angle like halfway, not quite all the way, and now when I turn the compressor, you can see that the pistons go back and forth, a little bit more, but not so much, not full stroke. If I turn the angle back all the way, if I change the angle of the back of the swash plate all the way to where we started, and now when I turn the compressor, you can see the stroke of the pistons is much longer. It's pumping at maximum capacity. So the whole idea here is if I can control the angle of this swash plate gradually, smoothly, seamlessly on the fly as the compressor is working, I can change the pumping output of the compressor gradually as the heat load demand changes on the system. So that's the basic, that's how internally, if we look inside one of these compressors here, this is actually how it works. So it's actually based on a much older technology, if you like. Now, the key thing to understand is how we change the angle of the wobble plate. And so if you look on the rear head here, I've got a control valve. So this is the old school pneumatic control valve. You're probably familiar with this. You've seen this control valve. It's held under the snap ring. You've been seeing this for many years on these old pneumatic variable displacement compressors. So the way that valve works, I've actually got one here. As you look at the valve, you will see that there's three areas in the valve. The fatter end here, the wider end here, which is going to be towards the top. There is a pneumatic bellows in here. It's through the hole. If I look inside here, there's a pneumatic bellows, a pressure-sensitive bellows. And so that area of the valve is exposed to low side pressure, evaporator pressure. In other words, the pressure inside the evaporator or in the suction line. And low side pressure, of course, is a function of the heat load on the system. If I move the blower speed from low speed to high speed, that's going to put more heat load on the evaporator. Low side pressure is going to go up, and that low side pressure is going to act on the bellows inside, and it's going to move a rod inside that's going to meter the pressures into different areas of the compressor. So the center section here is actually open to the crankcase. It's exposed, if you like, to the pressure in the crankcase area of the compressor. And the very tip of it, between these two O-rings here, that area of the valve is exposed to high side pressure. So the way this works is, as low side pressure changes, which of course is, as I say, is a function of the heat load on the system, as low side pressure changes, I can bleed more or less pressure into the crankcase. And by changing the pressure acting on the rear of the pistons, changing the pressure drop across from the top side to the underside of the pistons, I can change the angle of the swash plate. So that's how, by monitoring suction side pressure, which is a function of the heat load, I can change the pumping up displacement of the compressor to seamlessly, gradually, smoothly match the heat load on the system, right? So now we need to understand, well, how do we get to, this is a simple pneumatic valve. Well, imagine that I removed this valve, I took it out of here, and I replaced it with a computer-controlled solenoid. So you see that this solenoid, I've taken the O-rings off of it, but it actually still has the same three areas. It's got the area that's exposed to suction pressure, it's got the area that's exposed to crankcase pressure, and the narrow end of the tip of it here is exposed to high side pressure. But instead of just one input, if you like, low side pressure, function of heat load on the evaporator, we put the computer, it's just like an injector or an EGR control solenoid. By varying the duty cycle command to this solenoid, I can change the pumping displacement of the compressor in response to a whole much wider variety of inputs. So the computer can look at high side pressure, ambient temperature, low side pressure perhaps, cabin temperature, fan speed. The computer can consider a much greater number of inputs to decide what the pumping displacement of the compressor should be. And in fact, just a quick tip here, if a customer complains to you that their air conditioning is not as cold as it was last season and is using a compressor like this, an electronically controlled variable displacement compressor, then keep in mind that the econ button, that usually often a green button in the dash, the econ button, when you engage econ on most vehicles, it's going to prioritize fuel economy over cabin comfort. And so the computer will change the command profile being sent to the solenoid here, and the system will run a lot, the cabin cool down period would probably be much longer if you engage the econ function in the dash on the vehicle. So let me put this compressor away here, and we are going to discuss how we control. What does the computer look at to actually, in addition to some of the inputs I just mentioned, the two big inputs for computer control are, for the computer to control the command to the solenoid is, as you probably might expect, is evaporator core temperature. So the evaporator thermistor, the evaporator temperature, is a big input to the computer for displacement control. Obviously, we want the evaporator as cold as possible, but it can't drop below 32 degrees. So the computer is going to modulate the command to the solenoid to maintain the evaporator temperature in the target, at the target temperature. Another significant input to the computer is that this is the high pressure transducer. This is the transducer that measures actual high side pressure, and if the pressure gets beyond a certain point, if the pressure was getting too high, for example, the computer would reduce the command, the pulse width command to the solenoid here to reduce high side pressure in extreme circumstances. So they're the two key inputs to the computer for controlling the compressor solenoid. So let me put this away for just a moment. And we're going to move on to talking about how these compressors actually work. So as I mentioned, you've got clutchless versus clutch. And the other thing to understand about how these compressors work is the early iterations of these compressors, the solenoid were all positive side controlled, meaning the solenoid was permanently grounded and the computer changed the pulse width command on the positive side of the solenoid to change the pumping displacement of the compressor. However, on more later systems, or certainly General Motors and Nissan in particular, they typically ground side control their solenoids. So this is a typical, the solenoid is permanently powered up, and the computer is going to duty cycle the ground side of the solenoid to control the pumping displacement of the solenoid. Now, just backing up for just a moment here, this is the scope pattern. The red pattern is the waveform, the current waveform. You can see here it's about 0.7 of an amp. And the bottom pattern is the duty cycle control from the computer to the solenoid. This is a positive side control solenoid. So you can see it's on about 80% of the time, which represents about, the solenoid, the maximum current in the solenoid is about 1 amp, so 70-80% is going to represent about 0.7 of an amp is what you would expect. And as I mentioned, the GMs and Nissans particularly are now using ground side, because the solenoid is permanently powered up and the computer duty cycles the ground side of the solenoid. So let's talk about testing. How do I test? How do I confirm if the compressor works or if there's an actual problem with the compressor? So of course, as you might expect, depending on the year, the make, the model, the scan tool that you have, and so on and so forth, there will be a variety of most likely there will be some kind of bi-directional testing option available on your scan tool, as you can see in this screen capture here. I can actually test, I can bi-directionally test this compressor on a Chrysler by modulating the compressor current, or I can also choose to do it by using duty cycle command. So we've got a 2015 Chrysler 200 here in the shop today, 2.4 liter. We've already got the scan tool connected up. And so let's see what kind of diagnostic options are available, what kind of testing and bi-directional options are available for the ECV compressor on this car. So it's a 2015 Chrysler 200. We're going to do diagnosis. We're going to select our control unit manually. We'll want the HVAC control system will be under body. And of course, we're going to test, we're interested in the HVAC or the air conditioning system. We're going to choose that. Taking a little bit of time here. And we could look at codes and data and so on, but for today's exercise, I'm going to go to active test. And I'm going to choose compressor current. In other words, I'm going to use the scan tool to bi-directionally control compressor current and see what effect it has on data and see how the compressor responds. Now, I'm just going to show one piece of data in connection with this exercise, and that is going to be compressor command current. So I'm going to Go OK. And so now on the screen here, I've got compressor current and compressor command current. And right now, the current in this compressor solenoid, in the ECV control solenoid, is about 0.45 of an amp, just under a half an amp. If you look down the bottom of the screen here, you can probably see that there are a variety of bi-directional command options. I can choose to connect to command it at 0 amps. So let's go ahead and do that. And you can see the current command is 0 and the actual current is 0. Now I can go to 0.41 of an amp. And you see it's telling me the compressor current is 0.41 and the compressor command current is 0.34. So they're close, but there's a little bit of a mismatch there, as you can see already. So now I go to 0.8 of an amp. And you can see that, you know, I'm only at 0.69 on the command current, but the compressor current is apparently 0.82 of an amp. I'm going to jump ahead here a little bit and go right to 1.63 of an amp. And you see that it's telling me, the scan tool is saying the compressor current is 1.63. And if I go down the bottom here, it's saying the command current is 0.82. Well, let me go right to the end here. And I try to command 2 amps or 2.04 amps, and it says the test is aborted because the request is out of range. So I'm going to abandon the scan tool here for a moment because I see several problems. With this approach. The first thing is, if you understand how these solenoids work, the typical resistance of one of these solenoids is between is between 10 and 14 ohms. So if you understand 14 volts, 14 ohms, let's say, so the maximum expected current in one of these solenoids is only 1 amp. Yet the scan tool seems to be indicating that I could command 2 amps. So do you see how that using a scan tool like this, if I didn't understand the system well in advance, using a scan tool like this and apparently seeing an option to command 2 amps in the circuit, that could actually create a significant misdiagnosis. I could think that I should be able to command 2 amps, but I know from Ohm's law that the maximum current can only be about 1 amp. So there's a problem. The interface between this vehicle and the scan tool data, there's a problem there, and this could easily lead to a misdiagnosis. So I have an alternative method here. I've got a tool connected up to this vehicle. It's right here, and this tool is going to enable me to independently test the compressor function on this vehicle. So if we look here, the tool has 3 functions. It's got normal mode, it's got manual mode, and it's got also a resistance check mode. So I'm going to start a basic check here. If we turn the camera the right way, we can see if I hit this button here, I can check the resistance of the solenoid. And if you recall, I said between 10 and 14 ohms. Here I see 11.8 ohms, which seems to me to be reasonable. It's in the expected range for this solenoid. So now we're going to go ahead and start the vehicle up. And you see in normal mode, the tool is showing me the actual command coming from the computer to the solenoid. The tool is strictly an observer, if you like, on the circuit. It's just monitoring the command as it's passing through the tool on its way to the solenoid. The tool is not doing anything to the circuit. It's strictly monitoring the command from the computer. And you can see right now, it's only about 65, 70 degrees in the shop right now. There's very little heat load on the system. And so as you might expect, the duty cycle command is pretty low. It was 20% there, now it's 34, 35. It's a fairly low duty cycle command. And if I look over here at my pressures, you can see low side pressure is starting to come down a little bit. High side pressure is just around 200 psi. And that's because the fans have not come on yet. Well, I want you to imagine that this vehicle came in the shop and the command in normal mode was 0. There was no command coming from the vehicle computer. So I can go into manual mode, right? So now in manual mode, using the tool, I have taken over, I've taken the computer off the table, out of the picture, and I'm using the tool to take direct command of the compressor pumping displacement. In other words, I'm going to use the tool to send the command, the duty cycle command, to the solenoid, and I can watch on my pressure gauges to see, does the pressure actually change? So I'm going to start increasing the command, and if you see here now, watch very carefully, you see the low side pressure is starting to come down, and the high side pressure is starting to increase. In other words, 53%, 55%, you can see the duty cycle command increasing here, you can see the low side pressure dropping, and the high side pressure starting to increase as I change the command to the solenoid. So using a tool like this puts me in direct command of the solenoid, takes the vehicle computer and indeed the scan tool out of the picture, so I get a much more direct and real world sense of what is going on with the solenoid and also what is going on with the compressor itself. I can functionally test the pumping capacity of the compressor completely independent of the vehicle computer. That's the whole idea here. So let's go ahead, we're going to shut the car off and we're going to go back to our presentation and pick it up from there. So one other compressor that I've picked out here, this compressor here is what we call a TSB19C compressor. And you can see it's got a couple of things. If we look at the diagram here, if we look directly at the compressor, you can see it's got that displacement control solenoid in the rear head, just like the other ones we've looked at. It's got a displacement control solenoid in the rear head. The computer is going to vary the pulse width command to the solenoid to control the pumping displacement of the compressor. I've taken the clutch off, but this compressor does have a conventional clutch, so we can engage and disengage the clutch. But a couple of unique features of this compressor. The first one is this sensor here. This sensor here is what we call a belt lock sensor. And it works very similar to a crankshaft, cam or crank sensor. It is usually a VRS, a variable reluctant type sensor. And what it's doing is it's got two wires attached to it. It's just providing compressor RPM input to either the HVAC control module or to the engine control module. And the whole idea behind this sensor is this. Toyota, for example, calls it the belt lock sensor. And as the name suggests, what the computer is doing, it's monitoring engine RPM, it's monitoring compressor RPM, and it can sense if the belt starts to slip for some reason, or maybe the compressor is seizing, the computer can see a discrepancy between engine RPM, compressor RPM, and it will immediately shut off the clutch to protect the compressor, protect the belt, and so on and so forth. So that's the belt lock sensor. The other unique sensor on this compressor is this piece here. It's mounted on the discharge manifold, and it's what we call this little sensor right here. It's called a refrigerant volume flow sensor. And that sensor, as its name suggests, it's monitoring, it can measure the actual volume of refrigerant passing through the compressor, right? It's a Hall effect type sensor. It's got a 5-volt reference, a ground, and a signal wire, just like a TPS or an old school map sensor. What's different about it is the output, the signal output changes in proportion to the volume or the amount of refrigerant flowing through the compressor. So the computer, it knows ambient temperature, head side pressure, low side pressure, evaporator temperature, knows a lot of information about the operating system of the vehicle. It knows the command that it's sending to the control solenoid here, and so it can use the refrigerant volume flow sensor to see, is the compressor pumping the amount of refrigerant that I would expect, and it can use that information to fine-tune the command to the pulse width modulated command to the displacement control solenoid in the rear head. So if we look at it here, I've actually got a manifold taken off. I've got a manifold taken off this one of these compressors, and here's the actual sensor. It's a Hall effect sensor, and remember, the sensor itself does not actually contact the refrigerant. It's just clipped. The snap ring holds it to the discharge port here, and inside, the real works of it are inside this the discharge manifold. There's a tiny magnet suspended between two springs. In fact, I think if we go back to the presentation for a moment, I do have a picture of that. And you see that little, see there where it says magnetic piston? There's a little magnet suspended there between two springs. And there is there's a bypass passage running parallel, a tiny passage running parallel to the discharge port. And so as refrigerant volume flow increases, you get a bigger pressure drop. You get a pressure drop across the restriction, and the little magnet, the magnet is pushed back and forth, and it's the movement of that magnet that creates the voltage output change on the refrigerant volume flow sensor signal. It's typically, it uses a 5-volt reference ground signal, like a typical 3-wire sensor. Key on, engine off, the signal output voltage is usually around 4.3 volts. At a typical idle, hottish summer day, maybe around 3 volts. And if you took the snap ring out, if you removed the snap ring and just had the sensor flapping in the breeze, it would measure about 0.8 of a volt. The signal voltage would be about 0.8 of a volt. Now, this next pattern here, the bottom pattern, the green pattern, is a solenoid current. The top pattern is the signal voltage. And so in the first half of the pattern here, we're going, repeatedly wide open throttle on the accelerator. And as you can see, the computer shuts off the current to the solenoid, so the current goes to 0. And you can see when that happens, the refrigerant volume through the compressor drops and the voltage increases. So the voltage moves inversely or in reverse to the volume of refrigerant. So as refrigerant volume increases, the signal voltage decreases, and vice versa. So that's how this refrigerant volume flow sensor works. So I'm going to grab back my original compressor here, and we're going to share a few diagnostic tips before we move on. So as you can see here, I've got this, it's the clutchless version. I've got the clutchless electronically controlled variable displacement solenoid on board here. The first thing is these compressors, all these variable displacement compressors have a crankcase. And that means that you need, if you're draining oil from or adding to this compressor, you need to do it through the crankcase drain plug, right? And this is very important. It's very important if you're putting an engine in a vehicle or doing a motor swap, or maybe somebody's doing some body work on the system and the refrigerant has leaked out because the condenser was leaking, or maybe somebody's recovered the refrigerant from the system. It's very important never to run this compressor. Never start the engine or run this compressor with no oil in the system. With no refrigerant in the system. Because even though the compressor may be full of oil, we're depending on the refrigerant to keep the pot stirred. In other words, to agitate and keep the oil, keep all the moving surfaces lubricated inside the compressor. So it's very important never to run one of these compressors with no refrigerant in the system. Otherwise, you'll damage the compressor very quickly, very easily. The other thing, just going back to our presentation for a minute, Toyota has had some problems, 2012, 2013 Toyota Camrys. It may come in with this diagnostic trouble code B1479, which refers to that refrigerant volume flow sensor. And Toyota's recommendation here is to replace the entire compressor assembly. And, I often get asked, can the sensor be replaced separately? The problem first of all, I see a lot of inexpensive online sensors that do not work. They output a fixed voltage and the voltage does not change as the refrigerant volume flow changes, so beware of that. Also, sometimes it can be difficult to determine, is it a problem with the sensor or is it a problem with the plunger, with the magnet and the springs underneath? So by the time you've recovered the refrigerant, all the labor and the refrigerant expense that's involved, it's usually just more cost effective to replace the entire compressor as an assembly. Kia has also had some problems with the ECV solenoid and the evaporator thermistor, the evaporator temperature sensor, and their recommendation is that you can replace the ECV solenoid in conjunction with the evaporator thermistor to correct the problems with their system. So I just wanted to be sure that we understood the lubrication situation there. If I'm adding oil to or draining oil from this compressor, I need to do it through the drain plug. I mentioned this in our session last month. Cannot overemphasize the importance of choosing a quality oil. Good oils have a myriad of properties. They're end-capped, have antioxidants, metal passivators, anti-foaming agents. There's a lot of science goes into the development of oils. So when you're, when you're adding oil to one of these compressors, it's important that you choose the right oil. Don't forget also that if it's a R1234IF system, R1234IF, the refrigerant molecule is much more unstable. So it's very important that you use the R1234YF oil. The new oil, this YF oil, has a heavy-duty additive package to stabilize the chemistry in the system. So it's important to use the right oil in these systems. So, as I said, we add it through the drain plug, and don't forget, it's always important when we've added the oil before we ever crank the engine up. It's very important that we use a spanner wrench or a turning tool. I want to turn the compressor through 10 full revolutions by hand to ensure there's no liquid oil sitting on top of the pistons in the compressor that would cause a slugging event on startup. So it's very important to turn the compressor by hand at least 10 full revolutions before you try to start the vehicle up. Don't forget, just a small amount of resistance in the clutch circuit. This one, the one we just looked at, of course, doesn't have a clutch, but many of them do. Many of the later models actually do use a conventional clutch. So it is important, as always, to check clutch voltage with the clutch engaged. 1 ohm of resistance, of excessive resistance in the clutch circuit, will reduce the strength of the magnetic field holding the clutch engaged by almost half. It'll turn a 48-watt clutch into a 27-watt clutch. And so it is important to check the voltage at the clutch with the compressor engaged. I emphasize this point because often when you're working in the vehicle inside in the shop, there's relatively low heat load. 60% of the heat load on the vehicle is typically 60% of the heat load typically comes from the direct sunlight streaming through the windshield. And so when you're working in the shop, there's significantly reduced heat load on the system. So by checking the voltage, you're confirming that there's enough, that the strength of the clutch is strong enough to keep the clutch engaged the following day when the customer is in stop-go traffic, and high side pressure is 275 psi or maybe higher depending on the circumstances. So checking clutch voltage, very important. So I'm going to wrap it up here. I may have mentioned this last month, but I just want to remind everybody that that R134 has been phased down, not been phased out, but it has been gradually phased down. I think by the end of this year, it'll be phased down to 60% of our 2013 production. And therefore, it is important that we be aware of what's going on there. At the moment, there are 2 applications at the EPA. One is a blend called R456A. This would be a direct drop-in replacement. It's actually a combination of R134A, R1234ZE, and another product called R32. And the idea is that it would be that you could mix this refrigerant. It would be you could mix it with R134A in an existing system. It would be a less expensive option for maintaining an R134A system. The other option, however, that is being considered, and I think probably the more likely outcome, or probably the better solution in the long run, is R1234YF is now being submitted to the EPA. They're asking for approval to use R1234YF as a retrofit refrigerant in R134A system. So that's not a done deal yet, but it's certainly potentially possible by the end of this year. So keep that in mind. It may eventually be possible to use R1234YF, the new refrigerant, to retrofit older R134A cars. Don't forget, we remind you every month, and once again, go to 4s.com. There's lots of great, under the Technicians Resources tab, some great downloads available there. Check on our YouTube link, and halfway down the page here on the right, in that square on the right-hand side, enter the search term leak or ECV compressor. We've got several videos there on testing these compressors using that tool. So if you search for ECV or compressor, those videos will pop to the top of the list. And so some great diagnostic and technical information there on our YouTube channel also. So, recapping our session today, we talked about these electronically controlled variable displacement compressors, how they actually function, how they work. We explained some diagnostic approaches using a conventional scan tool and a special custom dedicated tool that really makes testing these compressors much easier and more direct. And we also shared some service tips along the way on lubrication and so on and so forth. So don't forget, next month, join us again next month, May 8th. The topic is engine operation, keeping it in time. I think you'll really like this topic, and don't forget to join us at the next month, and we will talk to you all then. Thank you very much indeed, and see you then.